Greetings and welcome to the Crystal Structures of Solids Lab, where we're going to introduce a little bit of the idea behind solids. Solids can be broken down to amorphous solids, which honestly are hard to predict and understand their properties, in my opinion, or what's called crystalline solids, and we're going to look at crystalline solids. So crystalline solids have small repeating units, and if you could shrink yourself down to the size of an atom, you'd actually see these things called unit cells. And there's a whole bunch of different unit cells. We're going to look at one very simple kind, which applies really well to pure metals on the periodic table. So it's kind of a cool lab, some different techniques we can use. Let's get into this lab and see what the lab can offer. So as I stated earlier, solids can be broken down into two general classifications. Amorphous, which is like clay and dirt, stuff like that. It's harder to predict the properties, so we're not going to talk about it in this lab. But a lot of solids are what they call a crystalline solid, which means they have small repeatable units in the massive sample. And what that means is that if you could shrink yourself down to the size of atoms and look at a sample of, say, copper or magnesium or chromium, whatever, you would see little tiny patterns of repeating atoms. And in the lower right-hand corner there, these are the kind of repeating units that we're going to see in this lab. And they're called simple cubic, face-centered cubic, and body-centered cubic unit cells. So, for example, in the body-centered cubic on the far right there, that little pattern repeats over and over and over again. Remember, there's 10 to the 23rd of these crazy atoms at almost any given sample. And in the sample that we'd be looking at, there would be just repeating unit after unit after unit and stuff in the system, which is pretty cool. So we'll talk about what that means. Why, for example, in the left-hand side there, you can see there's a body-centered cubic system on the right, but on the left-hand side, you see it's like been shaved off. We'll talk about what that means. If you understand how a unit cell works, then you can apply this to other systems. And a lot of biochemical systems and more complicated inorganic systems use very complex unit cells. But the idea is the same. It's these little tiny pieces that repeat over and over and over. And in this lab, we'll get to use some of the techniques that are used to understand how they go, how density plays a factor, Avogadro's number, stuff like that, which is really cool. In this lab, all of our unit cells are what they call cubic. And there's actually many different types of unit cells. But in a cubic unit cell, all of the angles are 90 degrees, and that makes the math a lot easier. So trust me, that's a good thing. Also in a cubic system, because they're cubic, the length is going to be the same for all sides. So if you wanted to find the volume of a cube, it's like side times side times side, or side cubed equals volume. That'll be important to us coming up. So let's look at what these different unit cells can offer us as we learn this material. This lab involves the unit cells of metals, or the metallic crystal structures. And these things are pretty common when it comes to metals. If you think of all the solids around you, all right, from the metal around you to the wood and everything else, most of the solids can be broken down into very small repeating units. And they call these little pieces unit cells. And unit cells just repeat over and over and over and over and over again. And for metals, there's only a couple different types of these unit cells we're going to look at. And again, this is a huge area of research, and we are just barely scratching the surface of it. But if you do end up doing solid crystallography kind of stuff, solid state materials, this may be helpful to you. So anyway, if you're talking about metals, which we are, most solid metals can be described using one of two unit cells. And the first one is called the body-centered cubic cell, which we're going to abbreviate BCC. Now in that picture there on the left-hand side, you can see two versions of it. And every one of those blue dots in the right-hand cube would represent a metal atom. So you can see that the metal atoms are kind of in the corners of the cube, and there's actually one right inside the middle of the cube. They call that one in the middle of the body of the cube, so that's where the body-centered cubic name comes from. A body-centered cubic cell is actually fairly common on the periodic table for metals, and I'll show you some information in lecture that talks more about that. But when you want to know more about the body-centered cubic cell, there's two things that are really helpful to you. It's helpful to know how many atoms there are in a unit cell, and it's also nice to know the relationship between the the edge, and in crystallography, the edge, which would be like the distance from that edge to that end, the edge is given the symbol D0. And I'm not sure where D0 comes from, but that's what I'm going to use so you're introduced to it. So when you're talking about a unit cell, you should know how many atoms there are and also what's called the edge to radius ratio. In that drawing, it shows the little atoms as like points on the unit cell. And in reality, a lot of the atoms are actually touching. Let's talk about the atoms first. In a body-centered cubic cell, that atom in the middle, that body-centered one, that's a full atom, all right? So BCC has at least one atom. But the atoms in the corners, all right, they're actually part of 8 different cells. Because if you can use your imagination a little bit, you could have a whole bunch of these unit cells like stacked together. And this picture on the left shows what happens when you want to find out just how much of the atom is inside the cell. If you shave off with like a chainsaw or something, you shave off the parts of the atoms which aren't in that little cubic cell right there, you can see how they look a lot different. Like most of the atom was shaved off. Those shaved pieces are part of the other unit cells in these BCC areas. So when all is said and done, those corner atoms are only 1/8 inside the cell. So even though the picture on the right shows those little dots and you think, oh yeah, okay, no problem, each one of those. No. The corner atoms are 1/8 inside the atom. So when scientists figure out the net number of atoms, you've got the one in the middle, you have 8 corners, and the corner atoms are 1/8 inside the atom. So 1/8 times 8 plus 1, 2 net atoms per BCC cell. We're going to talk about that more in lecture, so if this is a little weird right now, just kind of take it as a leap of faith and we'll do more in lecture. The other part, like I said, is the way to go from the radius of the atom to the edge of the cell, or from this edge to the radius, either way. And this has to do with geometry. And in the actual lab, I'll show some and I'll demonstrate how you get these relationships. But for right now, just realize that for BCC, the edge, D0, equals 4 times the radius divided by the square root of 3. And again, that relationship comes from geometry. You don't need to be too worried about it, but this is the way you can go from the radius of one of the atoms to the edge of the cell, and that's going to be really helpful to us. In BCC, we would say 2 atoms per cell, and the edge D0 equals 4R divided by square root of 3. The other kind of unit cell, which is fairly common on the periodic table, is what they call the face-centered cubic cell, FCC. And if you go through the same kind of analysis, the face-centered cubic cell has 4 net atoms per cell, and the edge of a face-centered cubic equals 4 times the radius divided by square root of 2. Now, face-centered cubic doesn't have the atom in the middle like the body-centered atom like BCC does. But if you look at that drawing long enough, there are lots of what they call face atoms, these guys right there. And a face atom is half in the atom, in the unit cell, and half outside the unit cell. So those arrows I'm pointing to, those refer to the same atom. You can see on the left, it was like cut in half, all right? Because the other half would be on the unit cell above. So because there are 6 faces on the cells, these cubic systems, and there's half of an atom in each one of them, 6 times 1/2 is 3 atoms, plus you've got those 8 times 1/8 corner atoms, that's where the 4 net atoms per cell comes from. So to summarize, everything basically we're going to do in this lab is going to be BCC or FCC. And there's 2 things you need to know. For BCC, you need to know that there's 2 atoms per cell and edge equals 4R divided by square root of 3. For the face-centered unit cell, the 2 things you have to know, 4 atoms per cell, as well as edge equals 4R divided by square root of 2. And again, if you're curious about this, I do encourage you to look in the lab for more information as to how these things come from. But as long as you are cool with it, let's move on and see what you can do. If you know the edge d0 and the radius and edge conversion, and again, edge is d0 and radius is r, and if you also know the number of atoms per cell, and again, all of these stuff comes from either if you have BCC or FCC, there's a really interesting pathway that can be used to find a lot of information. And this thing right here, which is kind of long and narrow, literally think about it like as a type of a train track. And you can convert, for example, the radius r to the edge. That's where the BCC or FCC comes from. And the reason people like knowing the edge, because if you have a cube, length, width, and height are all the same. So if you cube the edge to the third power, that's going to give you the volume of the unit cell. And because these are metals, we always or can calculate what the density of the metal is. And even though this is going to be a really small volume, we can use that density in order to turn the volume into the mass in the unit cell. And because we hopefully will know what the type of metal is, we'll be able to look up on the periodic table what the molar mass, the grams per mole value is, so we can turn mass into moles. And then finally, if you have moles, you can use good old Avogadro's number, 6.022 times 10 to the 23rd, to go moles into atoms, or if it's a compound, it would be molecules. But anyway, this is actually a pretty cool kind of pathway to figuring out different things. In the lower left-hand corner is the BCC summary, 2 atoms per cell, and the edge equals 4 times the radius divided by square root of 3. In the lower right-hand corner is the FCC summary, 4 atoms per cell, and the edge equals 4 times the radius divided by square root of 2. In addition to those two things, there's going to be some new types of units we need to introduce. In crystallography, a picometer is actually a convenient unit to use sometimes when you're talking about radii and edges, stuff like that. A picometer is another type of metric part, a pico. Pico is 10 to the minus 12. So a picometer would be 10 to the minus 12 meters. Remember that a nanometer in Chem 221 was 10 to the minus 9 meters. This is even a smaller unit of measurement, which is kind of cool. And then also in this area, we end up with what's called an angstrom. An angstrom is not really a metric unit, but it's easy to convert. Angstrom, I think scientists like because it's that cool A with the circle on top of it, but I don't know. I'm juvenile. But anyway, an angstrom, if you see it, is equal to 10 to the minus 10 meters. So it's just another kind of length, all right? It's not a metric conversion, but it does pop up here quite a bit in these sections. I'm sure at this point you're like, blah, 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 blah. You're hearing like the Peanuts teacher talk and those kind of cartoons. Let's go through an example to see how this all works out. Once you see this, I think it's going to be pretty chill, just like linear regression, all right? But getting started with it can be a little bit weird. So let's look at an example. This is the kind of question you might see in this section, and it says, what element forms a face-centered cubic cell, has a density of 12.3 grams per centimeter cubed, and a radius of 135 picometers? Okay, well, at first that would seem a little daunting, all right, because there's a lot of new terms here and they're not very familiar, and it's not really clear how these things all pop up, all right? So let's talk about the strategy that we need to solve this problem. First of all, this is an FCC, a face-centered cubic problem. And every time you see face-centered cubic, remember that means 4 atoms per cell, and the edge equals 4 times the radius divided by square root of 2. And remember, this is our radius, so you can probably see what one of the first steps is we're going to do here in a little bit. That's going to be the first thing. You got to know what to deal with and what FCC means. And FCC, or BCC for that matter, there's 2 things you need: number of atoms per cell and that edge to radius conversion. The second thing is that this pathway below is what you're going to use on all of these problems, all right? And if you follow this pathway through, it's not going to be too bad. If you look at this, we said earlier how we have the radius, so we can use the radius to edge conversion to get to edge, and edge cubed, whatever that number is going to give you volume, and we have the density up there, so we can turn volume into mass. However, we don't know what element we're dealing with here, so we can't exactly look on the periodic table for the molar mass if we don't know what it is. I mean, is it hydrogen or uranium or whatever? Who knows? So once we get to mass, we kind of have to stop, and then you go to the far right and move left until you stop again. So what that means is, hey, FCC, 4 atoms per cell. We can turn atoms into moles using Avogadro's, because even though it's a really small number of atoms, Avogadro's number still applies. So then we've got mass from our stuff on the left, we've got moles from our stuff on the right. Mass divided by moles, I'm sensing the identity of the element is going to come out if you look at a periodic table. Again, what I said there in a little bit more wordy version is first we're going to start on the left and go right as far as we can. And so in this problem, it's going to be radius to edge using the FCC part. Edge cubed equals volume. And finally, we can go volume to mass in grams using the given density. But then we have to stop, all right? We're kind of looking for the molar mass, all right? That's what we want to find. If you knew the molar mass, you could look up on the periodic table and tell how many grams per mole it was, no problem. But we don't know that here. So the next thing you want to do is you want to start on the far right and move your way left as far as you can. 4 atoms per cell, you can turn into moles per cell using Avogadro's number. It's going to be really small and a funky number, but it's going to be legit. And finally, if you have mass and grams and moles, plug them in. Grams divided by moles will give you the molar mass. And you can look it up on a periodic table, find the identity of the element, and you're good to go. So if you use this strategy and you use that little pathway down there, these problems aren't too bad, all right? They're kind of fun. Well, okay, look, I'm a chemist, all right? I think they're fun. But anyway, hopefully they're not too hard, all right? They're not dull. I don't know, maybe they are. All right, let's prop that back on. Anyway, you can totally do it. That's what I want to get across. Now, one more thing. Before you go from edge to volume, all right, wow, you've got to convert your picometers or your angstroms or whatever you've got to convert it to centimeters. And this is why the density is almost always given as grams per centimeter cubed. And if you cube a edge in picometers, which is what you would get by just plugging it into this thing up here, a picometers cubed to centimeters cubed conversion is possible, but it's a real pain, all right? So before you cube the edge, make sure you turn the edge from picometers into centimeters. And so I put up there the conversions again. 1 picometer is 10 to the minus 12 meters, and a centimeter, if you remember from Chem 221, 10 to the minus 2 meters, or 100 centimeters per meter. Either way is fine. But again, before you do that edge to volume thing, turn the picometers into centimeters, or if you have angstroms, turn those into centimeters, because the next part, having a centimeters cubed and a density in grams per centimeter cubed, gonna make your life a lot easier. So let's actually do this problem, all right? And the first things we're going to do, we're going to turn the radius into the edge into volume, volume into grams, and we're definitely going to convert picometers into centimeters sooner more than later, all right? At the very least, do it before you do the volume. You could do it right away, whatever you want to do. For face-centered cubic, all right, the edge equals 4 times the radius divided by square root of 2. So when I put this into my calculator and to 3 significant figures, I got 382 picometers. And by the way, at this point, I highly recommend that you go along with your own calculator and make sure that you're getting these numbers, all right? If you don't get the numbers I put up there, you let me know, because there could be a math thing going on. This lab has a lot of mathematical dexterity, just putting the numbers in a calculator correctly, which is actually an art unto itself. So if you aren't getting any of these numbers, please let me know. On the other hand, if you do get these numbers, then you've got all the skills you need to do this stuff. The length of the cubic cell is 382 picometers, and that's a very, very small distance, all right? That's the idea behind this. Now, before I'm going to cube my edge, because that's the edge number we're going to cube, I'm going to turn the picometers into centimeters. Now, a picometer is 10 to the minus 12 meters, and there's 10 to the minus 2 meters per centimeter. So when you do this all out, you get 3.82 times 10 to the minus 8 centimeters. And a centimeter is something you can kind of visualize. This is a very, very, very small number of centimeters. It's nothing you can see. This is the length, again, of the edge now, but instead of picometers, which is kind of weird, maybe this is in centimeters. Once you have it in centimeters, then you can do the next part, which is volume equals that edge number cubed. So we're going to take 3.82 times 10 to the minus 8th and take it to the third power. And if you get that, you get 5.57 times 10 to the minus 23 centimeters cubed. That is a really, really small volume. Remember that a centimeter cubed and a milliliter are the same. If you go and look at like a 12-ounce can of Coke or soft drink or something like that, those are usually, if it's like 12 ounces, I think it's like 355 milliliters. So this is orders and orders and orders of magnitude smaller than a milliliter. And every time you have a solid in your hand, whether it be a pen or if it's a Rubik's Cube or whatever, you've got really, you just have a really, really small unit cells inside there. And it also gives you a sense for how many unit cells there probably are. But anyway, neither here nor there. What we've done so far is we took the radius, we turned it into the edge, and we just cubed the edge to give us to volume. Well, we can do one more step using the density. We can turn that really small volume into a really small mass. So we'll multiply by the density, and again, you get a super small amount of grams because these unit cells are really, really small, all right? Pretty chill. Now, at this point, we've gotten to mass, and the next step, if we had the molar mass, we could turn mass into moles. But we don't know what element it is. We don't know the identity of it. So we have to stop here, and on the next slide, we're going to start on the far right at number of atoms and move left as far as we can. In the next part here, what we're going to do is we're going to start with the number of atoms. We're going to turn it into moles. And then once we have moles, the molar mass is going to equal the grams that we just calculated on the last page, divided by the moles we're going to calculate here in a little bit. So let's see how this works. So first of all, let's convert the atoms into moles. 4 atoms divided by Avogadro's number does give you a number of moles, and it's really, really small. Now, I want to make sure, especially at this part, that you're getting this number. It's easy to go 4 divide 6.022 times 10 to the 23rd, and your calculator may not be aware that you want to divide by 6.022 times 10 to the 23rd and not go 4 divided by 6.022 and then multiply by 10 to the 23rd. So if you're getting a very large number here and you're not getting 6.64 times 10 to the minus 24, it's because your calculator thinks you want to multiply by 10 to the 23rd instead of divide by 10 to the 23rd. So to get around this problem and to make sure that you do get this number, you can put parentheses around the whole thing. So 4 divide 6.022 times 10 to the 23rd would be one way, in parentheses. You can also use what I call the E or EE button, and calculators have this. It's a power of 10. If you go 6.022 E 23rd, that's a calculator's way of knowing that, first of all, you want to multiply by 10 to the 23rd, and also that you want the 10 to the 23rd to be associated with 6.022. If you look over here in this little answer, I'm always writing them as e to the minus or e to the plus, whatever. That's because those are the numbers that the calculators will give you. All right, it may say 6.6423 times 10 to the negative 24, but in the math world, this is real common. In programs like Excel, or numbers and stuff, if you're going to enter these powers of 10, use the E button. This goes 6.64 E minus 24, and that's what those programs use. So anyway, a lot of information there. Prof. back on. As long as you end up with this number, you're good to go. If you don't get this number, make sure that you reach out to me. I have something very important I need to share with you so that you get the right numbers. You've got the moles. From the previous slide, you've got the grams, the mass. So the next step, mass divided by moles. So the grams we had on the last page is that 10 to the minus 22 grams. There's the mole number we just calculated. And if all is said and done, you should get a molar mass of about 103 grams per mole. And what I would do now is look on the periodic table. You want the molar mass which is closest to 103 grams per mole, and I'd say that's going to be rhodium. Rhodium is 102.9055 grams per mole, so that's definitely pretty close to 103 grams per mole. I think you've got rhodium. Rhodium is usually worth more than gold, so if you really had rhodium, score! Unfortunately, this is just a virtual experiment, but darn it. Anyway, Prof. back on. So anyway, these processes, you can hopefully see how this works out. If the question ever asks for identity, that means basically find the molar mass. And you'll start with the radius and work all the way over till you get to mass, like we did here. Then you'll start on atoms and work all the way over to moles, then mass divided by moles, molar mass. I think one of the problems is going to ask you for the density. So you can start with radius, go to edge, and then volume, and then you have to stop. Then you go back to the right, the number of atoms for the cell to moles. You probably know the identity of the metal, so you can go moles to mass, and then mass divided by volume will give you density. So again, these problems, I think once you start seeing them, are not too bad, and we'll check them out in this lab experiment. When you're doing the crystal structure, I really recommend you use that little pathway down there. And this pathway comes straight from the lab. It's also in the lab itself. But if you follow it, you won't be in trouble. All right, you'll know what to do. You'll go from left as far as you can until you have to stop. Then you go right as far as you can until you stop. Good to go. That's really kind of what it comes down to. I certainly do recommend that you convert picometers or angstroms to centimeters before cubing. All right, just going to make your life a lot easier. And again, that's because the density is probably going to be grams per centimeter cubed, and you don't want to have a picometer cube to centimeter cubed conversion. Yes, you can do it, but it's just a big pain. So try to do that before. It'll make your life a little easier. I think in one of the problems, you have to go from a volume to an edge. So volume equals edge cubed. And if you want to get to the edge, you need what's called a cubed root. And cubed roots look like this on your calculator. If you have the symbol, it's a cubed, it's like a square root with a 3 right there. All right. And that's called a cubed root. As an example of how this works, 3 times 3 times 3 would be 3 cubed, and that's 27. The cubed root of 27 would be 3. So this is one way to test yourself and see, make sure you've got it. So 3 cubed is 27. The cubed root of 27 is 3. All right, just like 2 squared and square root of 4, et cetera, et cetera. Anyway, if you have that symbol in your calculator, awesome, you're good to go. You can also, though, take the volume and raise it to the 1/3 power. So if you had some number and you use a caret parentheses 1/3, that would be another way that you could do a cubed root if you need it. It's not something we'll do a lot of, but it is something we'll do once in a while, so it's cool to know how to do it. Remember that the cubed root of 27 is 3, and if you get 3 when you cubed root it, you're good to go. Those powers of 10, when you divide by them, can get messy. And if you're not getting the numbers we did on the example earlier, make sure that you put parentheses around the bigger and smaller numbers. The EE button is awesome. If I can see you, then I can show you on your calculator. It's so cool. I can't tell you how cool it is. But you can also put parentheses around things. Just make sure that they tell the calculator that you want that in the denominator and not in the numerator. It'll mess up your answers otherwise. And again, if you go through that example we just did and you are getting different numbers, I do want you to contact me. This is super important, all right? I don't want you getting stuck on this math stuff, all right? I want you to be able to think about unit cells and how these works, and ooh, you can find numbers of atoms in FCC and blah, blah, blah. So again, go through that example with your calculator, and the part or parts you're not seeing, all right? You're not getting the answers, then definitely reach out to me and I'll see if I can help. Also, the Learning Success Center, Avid Center, they'll be able to help you too. Okay, at this point, I think it's time to watch a quick video to see how you would find the density of the unknown metal in the lab. This is the one lab component for this part. Also, if you have any questions on any part of this lab, the manipulations or anything, please feel free to reach out to me. I'm happy to help. You can also talk to the Learning Success Center / Avid Center. They will help as well. So anyway, it's all stuff you can do. It gives you a good chance to be very powerful with your calculator, if you will, and the calculator will be your good friend. Okay, good luck on this lab. Thanks for being here and have a great day.